I will start within a few minutes. So let me start with some recap of the last week. So as you know, this is the problem solving session week 3 of the course titled as Sensor Technologies, Physics, Fabrication and Circuits. Just wait a second. Yeah. So my name is Shomnath Bhattacharjee. I am pursuing my PhD at IIT Jodhpur in the Department of Electrical Engineering. You can see about me from here. So my working area or my specific area is flexible and organic transistors for neuromorphic computing applications. Um, and my educational background, as you can see, is I have done my master's in electronics, and I have completed my BSc in physics with honors. And you can find more details from this. The class schedule is as usual every Monday from 7 to 9. So this is the basic course layout of this course. This course is divided in 8 weeks, and the first week was basics of transistor. Sorry, just wait a second. uh, Basics of transistors, basics of sensors. We have done that part where we have learned what are sensors, what are transducers, what is the difference among themselves, and how do we know in which case we need to use a specific sensor or not. Then in the next subsequent week, we have learned about the parameters. What are the key parameters to characterize a sensor, if the sensor is working perfectly or if the sensor is lagging or something like that. So these parameters were resolution, accuracy, these kind of a things. And we need to know how to characterize your sensor, if the sensor is perfect for your application or not. Is it worthy to like invest some few more monies to buy a better sensor in terms of maybe resolution, in terms of maybe working range? Let us have an example. If we were working with an temperature sensor, we need to know the temperature on and around about 50 to 100 degrees centigrades. So there's no need to waste your extra money to buy a sensor which works in the domain of maybe up to 500 degrees centigrade. So these kind of things we have already learned. So this week we'll learn about the physics of the sensors. So already we have classified the sensors in various parts, like based on the principles like capacitive or resistive or impedimetric or something like that. But we'll delve deeper into the capacitive and the thermal sensors in this domain. And so this is our this week's layout. Yeah. So this module is known as the physics of sensors, where we will learn about the capacitive sensors and the thermal sensors. So let me start with this. So a basic one of the easiest to fabricate sensors are the capacitive sensors, and these capacitive sensors everybody knows about these basic capacitors. So just wait a second, yeah. So there is a basic capacitor which has two terminals, and it kind of looks like this. If we are considering a capacitor as a parallel plate capacitor where there are two plates. First is a conducting plate on top of this. There may be some material in between these two plates, or there may be air or something like that. So this is a basic structure of a parallel plate capacitor, which is shown here. That is, and if we just take the distance d here already noted. So this is a parallel plate capacitor which can work for so many different applications we can use it for. So there can be a material in between, or there can be maybe directly air or something like that. So the first thing to know about this like capacitive sensors is that we are using the capacitance phenomena. So there won't like there shouldn't be any interference from the resistive phenomena or the inductive phenomena. So it should be purely capacitive, otherwise we can't say it as a capacitive sensor. So yeah. So one of the most maybe used sensor we can say is the touch screen. Everybody uses smartphones, smartwatches, or some kind of things like even our laptops can be like touch control and everything. So just wait a second. Yeah. Yes. Yes, so like nowadays everybody uses a smartphone or something. Everything has a touch screen. So this touch screen, everybody knows that previously it was resistive touch screen where we used to like press with our thumb, and with the thumb itself didn't work. So we had to use our tips to like scroll through the phone or something like that in the early ages. But right now everything works in the capacitive phenomena. Why? Because it's faster, although it costs a bit like higher than the resistive ones, but it works much smoother. For like advancement of electronics, we need a capacitive sensor, a capacitive touch screen which will work faster than the resistive ones. So we know that from the like earlier ages, the price of these phones or the smart handle devices has increased. But this kind of a thing it brings, like if you are putting a capacitive sensor within your phone or something like that, it will have much faster response. If you are tapping your phone and it works after, let's say, 10 minutes, 15 minutes or something like that, you will be obviously angry. But in case of capacitive sensor, like we can scale it down to like seconds. Within a second, if it works, it will be like it will be also like you will be angry with that kind of a response, but it will work within a nanosecond or a microsecond. You won't have any issues with those kind of a things. So a touchscreen is made out of a covered glass, because we can't directly touch the sensors. So we need a protective cover glass which should be anti-reflectant, because as we are seeing some kind of a things, if it's anti-reflectant, if it has a like anti-reflection coating or some kind of a thing, so it will be helpful. Then the touch sensor comes here. That is our main part, which is a capacitive touch sensor. And then there is the LCD panel, which will just what do I say, like which will store your responses in whichever place you are pressing that. It will store your data, and then it will move on to the microcontrollers. So if we move forward to this kind of a touch sensing like cases, so this is a basic touch sensor. So how does this kind of a touch sensor works? First we need to know what is the basic structure of a touch sensor. So let me just wait a bit. So it's clearly visible that there is a lens and casting, and on top of that there are the sensors. So if there is a sensor like this, whenever you are putting your finger on top of this, it changes something. In case of resistive sensors, let me say this is a panel where this material is a resistive material. What will happen whenever you just put pressure on top of this kind of a thing? What will happen, the resistance will change. If like in some cases the resistance can decrease, in some cases the resistance may increase as well. So what will happen, in the first case, when there is no applied force or pressure or something like that, the resistance will be R1. And whenever there is a, like, maybe there can be a bump like this, so with this change in like pressure on top of these resistive sensors, the resistance will change to R2. That is, with this pressure, applied pressure, resistance changes to R2. So what will our microcontroller do? Our microcontroller will calculate this changes in the resistance, and it will like record a response for your touch to a specific place. So what happened in the earlier days, our finger will touch a single area, and what will happen due to that, that with the force, you need to touch with the force, like only just touching, or just like I can say, like with a better word I can say that you are pressing your device. With this, that press, there should be a structural deformation for us, like for a certain amount of time, and due to that the response will be recorded. But in this case, in case of like capacitive touch sensors, what happens, that your, obviously everybody knows that our hand, it can be considered as a capacitive material. What will happen, so the pathway for the current will change with respect to your touch. So you don't have to press on the press on the sensor itself, you just have to touch on it, and by the touch itself there will be a change in the capacitance. And the microcontroller will, what will the microcontroller do, a microcontroller will just sense this change in touch. And we can also specifically know, because we can say with a like resistive touch sensor and a capacitive touch sensor, there is a huge issue with that. Because like if we say capacitive touch sensor is like this, we can divide it with like 9 grids. So there are 9 grids. If we press here, the response will be recorded here. If we press here, the responses will be recorded here only. As we are not just pressing on it, we'll just touch on it, that's it. So we can like quantify the amount of touch, like we like applied or something. Like in case of like Apple Pencil or some kind of a thing, if we touch the touch the device with similar like small amount of pressure, the response will be like this. But if we touch with a like a more pressure, if we apply a bit more pressure, the response will be like this. So just wait a second. So the response will change with respect to your touch. But what happens in case of a resistive sensor? With a resistive sensor, we'll do the same. This is the resistive material, and we'll just divide it with like 9 equal. Obviously, like my drawing is a bit off, but like it will be in like 9 equal parts. What will happen if we touch on this one? The peripheral like this squares, like this one and this one, the touch will be recorded here obviously. But to increase the sensitivity, what will happen, there will be a slight deformation in this place as well and this place as well. So due to that, there will be a smaller response in those cases as well. So to negate that, we need a better microprocessor which will like negate those kind of issues. That's why we'll just like reduce the sensitivity. Otherwise this places will also record this kind of a phenomena. So that's why moving towards a like capacitive touchscreen was necessary. Now just sorry. So wait a second, before this I have to explain something else. Yeah. So other than this, like we can just create a um, maybe here I can draw that. If we have a microcontroller like this, and it has two pins, maybe P1 and P2, we can connect a touch sensor here, and what we can do that we can add a we can't have a like zero capacitive circuit or something like that. So what we'll do, first we'll add an resistance here, and after that we'll add an capacitance here. Let's say the capacitance is C and the resistance is R. So when there is no pressure applied in this condition, there will be a certain amount of capacitance, that is only the C value. But when we touch this, just wait a second. When we touch this sensor, there's an induced capacitance of CF. That is the capacitance of the finger itself. The microcontroller, yes. So there will be a change in capacitance, and this change in capacitance, that is the del C, is calculated by this microcontroller, and it will give response to how much amount of pressure is applied to your device, or that specific area, and how the change in this change in capacitance, there may be change in capacitance due to like a different finger press, or a different area press. Like if we are pressing here exactly, there should be like a different kind of a response, and just like here there should be a different kind of a response. There should not be any kind of a, like interference happening from these cases. So now moving on to a like more advanced topic, that is the multi-touch sensor. So how does a multi-touch sensor works? Any ideas? As we know that the basic touch sensor works with like, if we divide the sensor with like, let's say with 9 different grids, depending on the grid you touch, it works. But what will happen with a multi-touch sensor? Because if we press here, let's say on sorry, just change the color. Yes, if we press on the first one, it should change a capacitance of C1 maybe, and we'll calculate del C1. And if we press here, the we'll calculate the case of del C2. But if we press on both of the cases with simultaneous pressure or something like that, what will happen? How will it work? Any ideas? How a multi-touch screen works? Any one of you can like maybe try, like you don't have to be so specific that it is doing like this or it is happening like this, but you can just try. Or maybe you can type in the chat as well if possible, if you are having issues with your mic or something. Yeah, others? Because let me give you some details maybe. So in this case, like even if we divide those things, we won't have this kind of a two different responses with different scenarios. Where we are pressing in a place, we can get a del C1, whereas we if we press on a different area, we will get del C2. But if we press both at the same time, there will be a newer change, that is C3. So we'll get del C3. We won't have any cases where we can calculate where have we pressed it. So, is there any way? Let me give you an example maybe. So what happens in a like LED display? A LED display is an array of devices where, like, let's say we if we have like 3 by 5 array of this devices, what will happen? Each LED works independently. So if we want to know that if we want to display a number that is 1 maybe, so what we'll need this 4 LEDs, no sorry, this 6 LEDs to light up, then we'll get to know that the value is 1. That's it. So what will happen if we try to use this kind of a technique in case of multi-touch sensors? I am explaining this kind of a things like through an application, because like rather doing directly from theory itself, like how the capacitors works, or how like accelerator acceleration sensor, like or a proximity sensor using capacitive like capacitive frame works. It's like a very like normal thing. But if we learn from directly from a direct sensor that we use every day, like a smartphone, everybody uses a smartphone and it has a touch screen. So like we can know that how this smartphone is working, at least from a single perspective itself, like how the touch sensor is working, or the how the screen is working itself. Previously in the older generation, phones have only single touch. If you touch at the like at a like how do I say, two ends of a device, it won't work. Then came a generation where only two touches or three touches work, not a multiple touches. But right now there we can press like multiple fingers, like in trackpads we can just do this and there will be a zoom in feature. So how do you think, just guess it, like how to like make us something like this from this kind of a phenomena, but make us something that's able to detect your multiple touches. If you're pressing with a finger on a different side, and if you're pressing with a like another side, so it should work. Any ideas? No. So I'll explain it. So what happens, we can always divide these sensors in multiple cases, right? But a microcontroller won't be able to do this. So in some of the cases, not in the newer generation, there we have multiple levels of sensors. So what we do that, there are two approaches. Let me say the first approach first. What they can do, there can be a level of capacitive sensors. In between there can be other peripheral devices and those things. There can be another sensor, just a sandwich structure, where the first touch will be directed by this and the second touch will be directed by this. But with this kind of a this kind of a architecture, the problem with that is it would be very costly. Other than that, there will be another issue, that there should be a limit, like we can obviously add something like this, but this kind of architecture would made it like a broad, like thick structure. But we are going towards a smaller structure, so we can't use this kind of a technique, right? So the second technique, what's normally nowadays applied, that we attach separate touch sensitive sensors, capacitive sensors, side by side, but a single microcontroller is connected with all of those. And this kind of a array, what will it do, it will also remove the issue with the neighboring, neighboring structures, that with pressing this won't have any kind of a interference or something like that. So this is the usual way to do it, but remember that it's very costly in any of the senses. Like if you are using smaller sizes of multiple sensors, it should be very costly, and reducing the size of the sensor will make it even like costlier. So we'll move towards the thermal sensors. So this is the thermal sensor. Thermal sensor, everybody knows that most common thermal sensors are the thermistors. So like I have nothing to say about these things. there can be like two types of thermal sensors, like in case of thermostats at as well. So like there can be a negative temperature coefficient, there can be a positive temperature coefficient, and depending on that we can use those things in like different kind of applications. But what's most interesting, like if we are taking a direct application from daily life, anybody knows not like from the thermistor itself or something like that, but interesting approach to use the thermal sensors in some kind of a different kind of a thing, with AC. Like we know that there is a thermal sensor with a thermometer. We know that it can be used for measuring the like your body temperature or something like that. But do you know any kind of a interesting thing where a thermal sensor is used, where the general sensor in that domain which is used, thermal sensor gives us separate separate domain where you can use a thermal sensor but not that sensor itself? Any ideas, any interesting applications of a thermal sensor? Just give me examples of thermal sensors, maybe. That will work fine. Any examples of thermal sensors will work. Maybe in daily life or something like that. That will like that will be like something unique or something like that. Any idea? Other than the thermometer or like thermistors in AC or something like that. Hmm. Let me give you an example maybe. So one of the main example I thought to is water heater. Yeah. So water heater, yes, you use it in daily life, but it's just only giving you temperature. I was thinking of something unique like a thermal sensor. Everybody knows about the thermal sensor, right? So in a thermal sensor, what happens? In a thermal sensor, we use the thermal sensor for imaging purposes. In general, we use an optical sensor which can detect any light or something like that. Like optical sensor can be in any ways possible, but a thermal sensor gives us image based on the temperature of that body. Like it can be a like instrument, it can be used in case of maybe military purposes. If you are searching for someone, um, like within a wood or in a like what do I say inside a debris or something. Like if a person is buried inside a debris or something, we can use a thermal sensor and we can get the temperature of his body, and we can directly locate where the person is, or whoever is is buried or something like that. So in case of marine, it's a very useful thing. So in case of marine application, its use is huge, because in case of like freezing waters or something like that, you won't be able to check and go and check each and every nooks and cranny, right? So you won't be able to detect where the problem of that ship is happening. Like if the ship is what do I say, like having a leak or something like that, so using a thermal sensor you can directly detect where is the leak or something like that, because the cold water will flow from that side. If let's say, not in this case, I'm just explaining you, if let's say there is a blue spot or something like that, what will happen, the cold water will flow from this side, and making it like while it's flowing, the metal of that area will be very freezing. In like it should be like in like minus 40, 50 or something like that. What will happen, we'll get to know the temperature of that area. If there is a very what do I say, like freezed area or something like that, the puncture will like freeze over the time because the chilly water is going through it. In this case, if we say, like, you can see that there is a heating issue with here. So if there is some kind of a machinery or something like that, so what will happen, the machinery is malfunctioning. Due to that, it's storing some kind of a heat. So due to that, we can also know where is the malfunctioning is happening for, like maybe there can be a leak or something like that. But in like chilly waters or something like that, you won't be able to go and check every place, like which place is having this kind of issue. But just having an image directly from a thermal imaging, or like we can say like in thermal vision or something like that, so we'll get to know where the problem of this thing happens. Now, why I am just explaining this kind of a things, because like recently COVID has like made a huge massacre and everything. So we can detect COVID from this kind of a things, because like testing each and every individual is was not available at that time, because at the starting cases we didn't know how to detect it, or exactly in which method we can detect it. But so what we can do, like if we have a batch of humans, like 10, 20, 50 humans at the same time at a place, we can use a thermal camera which will give us that this human is having a fever. So because of that, and at which spot like he has the malignancy or something like that. So like if his or her hands is like hot or something like that, we can get to know something about that. If his body is like heating, like this kind of a situation where we can see that the whole body is like above the normal like average temperature of that case. So we can say that just by using a thermal camera, out of 50 people, like two people have the symptoms. It can be a normal flu, it can be like normal fever or something like that as well. But we can, at first we can just separate them from the other. So like the rest will be like, we can say that everyone has a blue, and like if we are saying that the colors or something like that, so others will be in blue and like greens, while a single or like two persons are in like red color of imaging. So by taking just a simple image, within a few minutes, within a 1 or 2 minutes, we will just able to check the image, and we'll get to know whichever person is like having fever or some kind of symptoms like that. So it's a very useful thing, yeah, so it's a very useful tool we can use to use to capture images. And thermal imaging is a like revolutionary idea. And like in case of military, in case of like even if we are searching for a specific bomb or something kind of a thing, in those cases as well, because if you go there and it may it may cause some casualties or something like that. But if you are using a thermal camera, you can easily detect where the bomb is or some kind of a metal object is there. So so this is the basic principle of thermal imaging. What happens in case of this? So we have a thermal imaging device that has so many parts, but what is the most important thing? That is the thermal sensor inside of it. And this thermal sensor is detecting the IR waves. Normal camera is able to detect only the visible range. IR ranges are the just what do you say, like just above the red ranges. And there are few different IR waves, and out of those IR waves there are NIR that like normal people know normally, that is the near infrared range. Other than that, there are other two ranges, that is the mid infrared range and the far infrared range. Even if we are able to detect this NIR and MIR, but this is the most important thing, but we'll need to use in case of detecting an image or capturing an image using a thermal sensor. So what will happen if we have an this kind of a like image, like in if we can see that image, we are just detecting this MIR, FIR and NIR. Using those things, we can detect an image like this, we can plot image like this, which will show the temperature of that animal the temperature of the that you can clearly see that this is the basic temperature of the environment, whereas there is a slightly reduced temperature in case of this trees, right? Because the trees will be colder than the environment, because the stems of the trees are like a bit colder than the environment. Other than that, but this image shows that the animal is in white because of the temperature he's like what do we say, like he's just giving off. So like we can directly know that even like in a dark environment you won't be able to see this image, but using a vision like thermal vision you can directly see what's happening in here. So we'll move on to some questions. Let's see if some of you can answer this. So there's a parallel electrode capacitor, that's the parallel plate capacitor, as I was like explaining these things. Yeah. So the dielectric material in between this capacitor is epsilon, is termed as epsilon, is a function of temperature with temperature T. It is a function of T, and let's say epsilon is K by T as mentioned here. So find the sensitivity of this sensor. What is the sensitivity of this sensor? I'll give you maybe 2-3 minutes. Let's think about it. And also if you have any queries regarding the examples, so about the capacitive sensor or the temperature sensors, you can say that right now. Other than that, we'll have like a discussion around the last 15-20 minutes. So if you have any questions, we'll just consider that there. Yeah. What is the basic equation for an parallel plate capacitor? Like this capacitor, if the distance is let's say d, what is the basic equation for capacitance in this case? You already know the epsilon. Anyone trying to solve this? If you are doing, then I will give some more time. It's not that much visible. K by T. The basic equation for a parallel plate capacitor is that C is always proportional to 1 by D with change in D, and also always proportional to the area. So the basic equation is C equals to Ka by D. Now you may be able to calculate the sensitivity. Ka by Td. Okay. What is T? What is T? You are saying it's Ka by Td, right? So what is T? Temperature. Okay. So let's say here you already know that with respect to temperature, epsilon changes, right? So just wait a second, got sampling. So it's T. It will be T, right? Correct. So what will be the sensitivity then? What will be it? We already know that C is equals to K by Tt. Then so how to calculate the sensitivity? First answer this maybe. What is the like definition of sensitivity then? What is the definition of sensitivity? Difference between input and output, di by du. Um, Not exactly. Like you are very near, but not exactly. The ratio of the difference between input and output, that's perfectly fine. But is it the difference between input by output or something else? So in this case, what is our output and what is our input? What is the output value? It's a parallel plate capacitive sensor. Let me specify that as it's a capacitive sensor, anyways the output will be C, and we need to judge the value of this C with respect to T. So your answer was wrong actually. The difference in not that the variation in C, that is the output, with the variation in T, that is the input. So what is the value of this? What is the value of del C by del T? Everyone is doing this, or should I give the answer? So the basic answer will be Ka by dt square. This is the sensitivity value. Depending on the T, the sensitivity will also change over time. So if you increase the temperature, the sensitivity will decrease, and with decrease in temperature, the sensitivity will increase. So we'll move to the next question. So answer this question. Capacitive sensors can be used to measure what? And maybe you will have to give me some examples for each one of that. If it can measure position, if it can measure the acceleration or something like that. Just start with this question maybe. So can it measure position? Is position like measurable using a capacitive sensor or something like that? Anybody wants to answer? Like it will be fine if you like give a wrong answer as well. So it's perfectly fine. Position, yes. Can it measure or not? I'm not able to understand it actually. So maybe in the lectures you have already see this kind of a structure where we are having a parallel plate capacitor. Within this layer there is a material. There is a metal plate and this is the metal plate. In many cases we say it as the MIM structure, metal insulated metal structure, where there is a rod maybe, and by using this rod we can measure this position. What happens if we have a rod or a scale, we can use it as a scale or something like that. It's in X, that is at the 0 point. If there is like if we just press this device on the wall or something like that, there will be a shift in this material, in this insulator place. So what will happen, the structure will look like this. So if there is a new material in this position, it can measure the value of C here, and if there is only air itself, it will have a value as well. So with this C1 and the previous C2, this was, if let's say C2, this will be a fraction of C2 right now, some kind of fraction of this part. So with this variation in C, we'll get to know the exact position of the this marker or something like that. If let's say if it's marking the like distance, or it's measuring some kind of a height or something, so we'll be able to use this for measuring some distance or something like that. So we'll able to know the position exactly. What about acceleration? Can we measure you like a capacitive sensor can be used for like measuring acceleration or something like that, as we already know that we can get the value of position. Just give me a minute. You'll just think about it. Everybody knows about the accelerometer, right? How does it work? Any idea how the accelerator works? In everyone's phones nowadays, every phone has accelerometer. Um, Maybe I can skip on to just leave the accelerometer here, but I can say that already I have mentioned how to like use like how can we use to measure like temperature or some kind of a thing using a capacitive sensor. So how will we do it? We'll just have some kind of a temperature sensitive material which will maybe expand with temperature, or maybe like or shrink with respect to temperature. This middle part may shrink or may like expand. It can be like this after some time, so there will be this space remaining, and with there will be a reduction in C as well. So with this change in C we can measure temperature. What about accelerator? Can we measure acceleration with like temperature like capacitive sensors? Anybody want to try if like how to use it or something like that? I'll give you the answer. The answer is yes, we can use it, but the main answer will be all of the above, and the acceleration is yes. So any idea how to use a capacitive sensor to measure this kind of a thing like acceleration? Think of a let me give you the answer. Think of a structure like this, where we have like a connecting structure, connecting structure, and we have fingers like this. Just do it. So we'll have fingers like this, and this is like a kind of a like moving structure which will be able to like move with the change in velocity. So what will happen if we can create like some fixed structures in between this and this? This is a fixed structure, whereas this can move. So in the next case, like the position can be like this. It will be here, it will be here, and it will be here. So what will happen if we measure the capacitance in measure the capacitance in between these arms? Let's say this is an arm, this is an arm, this is an arm. So at the first position, if there was the arm here, what will happen? We'll get to know this total amount of capacitance, that is C. So we can measure C1 from here, and we can measure C2 from here. So like we can know exactly the what is the value of C here. But in the second case, while it's in a different kind of a position or something like that, what will happen? That this arms will remain at the same place, but this movable object, this case, what will happen that it will stay like here or something like that. Let's assume a position maybe. So what will happen? The total C will remain same, while there's a change in C1. C1 changes with respect to this movement, and C2 changes as well. So by this change, by this calculating this change in each of the arms, in each of the cases, we have to calculate this. By calculating this, we can measure the amount of acceleration device is gaining. So while using the phone for like a movable something, like if you're using it for like games or something like that, or like if you're moving on a like moving train and you need to know the acceleration of that train or something like that, so you can use this phenomena like capacitive acceleration sensor to measure this. even in like cars, like in Teslas or something like that, they have a very precise accelerometer. Obviously not this kind of a simple structure. They will have a huge structure with so many small like we can have multiple this kind of sensors, and we can verify the acceleration as well with respect to each of the sensors if they are giving the same values or not, because in like in a car, a self-moving car or something like that, so you need like security that the acceleration is exactly same which you are like trying to achieve or something. So this is it. So the answer will be all of the above. A capacitive sensor can be used for position sensing, a capacitive sensor can be used for acceleration measurement, and a capacitive sensor can be used to measure temperatures as well. Yeah. So is the next question. Try to answer this. What will be the sensitivity of the previous sensor if the let's say, just wait a second, maybe we'll move on to this one afterwards. We'll back because that will be a very similar question. Let's say if we have an IDE pattern. What is an IDE pattern? IDE pattern is a pattern like this, already I have shown this structure. It's called an IDE pattern, interdigitate electrode pattern. There can be numerous fingers or something like that. Let's say we have this kind of pattern. Okay, so there are 10 electrodes, they have already mentioned, each with a capacitance of 0.9 picofarad. If the distance between two adjacent electrode is only 50 micron, distance among each electrode is 50 micron, and length is 2 mm. So what is the thickness of the electrode? How to measure the thickness of this? So maybe I'll create a better image for understanding. Let's say the finger is like this, another finger is like this, another finger is like this. If let's say the finger is like going through this, so they have already given the length of the finger length is 2 mm, and within these two like fingers the value is 50 microns. So what is the thickness of this? Let's take up at least I guess 5 minutes, and then we'll discuss the answers. How can we like measure this? I've got the number of like electrodes in number of electrodes, that is the 10. How to measure this? So maybe I'll give a hint. Maybe the capacitance of this whole structure is calculated by using this formula. We already got the number of like fingers, which is n. What is the value of epsilon? And we need to calculate the value of d and a. D is also given here, the space between this. So this is the value of d. We have got the value of n. We just need the value of these two things. I'm sorry, questions. This is epsilon r is 50. Anybody is trying to solve this? Like how to get the values? You can also like guess that as well. Like how to get the value of a, how to get the value of epsilon. Maybe I'll write this. So this is 9. This is the value of epsilon, the value of a, and this will be the value of, yeah, how to get the value of a and how to get the value of epsilon. Please try at least, like if you are, even if you are wrong, that will be fine. Just try to answer this.
See, epsilon is equal to epsilon naught into epsilon r. Epsilon r is given 50 and
50.
epsilon naught is a constant, right?
Yeah,
8.854 into the power of minus 12. So we can find out epsilon.
yeah, epsilon is epsilon naught into epsilon r, and we know the value of epsilon r, that is 50, and this is 8.85. Oops, sorry.
Yes, 8.8542 into 10 to the power of minus 12.
Yes, yes. What I'm doing? Sorry. Yeah, it's perfect.
So, okay. And whereas A is the area of the plate.
Yeah,
So length of the plate is given and
that is 2 mm.
thickness, if you multiply, yeah, if you multiply by the thickness, you will get the area. And in our case, only thickness is, sorry, length is available 2 mm. with that we can find out thickness. Only thickness is unknown, right?
How? Like area is length into
There
thickness,
is
right?
thickness.
Huh?
So all the remaining terms are known to us. Only
Yes.
thickness is unknown.
Yeah. So what's the value of C here? Have you calculated that or
Hmm.
so if we put it here, the value of A will be 50 into 10 to the power minus 6 into 0.9 into picofarad divided by 9 into epsilon, that was 50 into 8.854 into 10 to the power 12. So this value will be, let me calculate, so the value is 0.11294 into 10 to the power minus 7. It will be in meter square. Yeah, so what will be the value of thickness? Let me recheck again, maybe 0.9 divided by 9, 8.854. Yeah,
No, 2 mm is missing in the denominator, right?
yeah, that is the length. Yeah, is the length of that. So we'll just need to divide this. Nothing else. Thickness is, yeah. Can you repeat again? Just give me the value. So in my calculation would be maybe 5.647 into 10 to the power minus 6 meter, or we can say 5.647 micrometers. Is it okay? Everybody has got the same answer, right? So, so what we have done until now, we know the value of D here directly. We know the value of this length, let's say length, that is 2 mm. We know the value of n, we know the value of epsilon r. We have calculated the value of epsilon, which is epsilon naught into free space permittivity into epsilon r, that is the relative one. So we know the value of relative one, and already epsilon r is given in the like in the question itself. So we have calculated the value of epsilon here. That is nothing but n minus 1 into epsilon into a by d. We know the value of d. We know the value of n minus 1, that is 9. We know the value of epsilon right now. So we have calculated the value of a, that will be this value. And after that, we know that a is nothing but length into thickness. So the value will be this. So it's an easier one, but in like real life cases, like I'll give you an error with this like question itself. So what happens in real life cases? So there's also this amount of area as well, right? This is another area. So if you are considering the finger length, you will only consider up to this. But there are some areas which needs to be considered as well. But for the simplicity purpose, we don't need to like determine these areas or something like that. But I am just giving you the thing that we may need to calculate some in some cases as well. We'll move to the next question. So we have a temperature sensor which has a heat loss of 0 in the environment. If the sensor is attached to an object, with an object it's tightly attached. So we
Excuse
must,
me.
yeah,
And you told one question number three, na?
yeah,
I mean, after question number four, we can see question number three.
yeah, yeah.
Is it?
No, 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 not
No.
after four. So like, actually, I rearranged the questions a bit because like I was having all the what do I say, like numerical
Okay,
questions,
no problem. Okay, okay,
not
okay.
random.
Carry on, carry on.
Yeah,
Thank you, thank
fine,
you.
fine, fine. Yeah. So we have a temperature sensor that is like this. It is attached to an object, something like this. So we need to know the temperature of that object itself. So what's happening in this case, that um, we need to know the temperature of the object itself, but after a certain amount of time, that is, we can say that one thermal time constant, we need to know this value. The initial temperature of the sensor itself, the sensor temperature was 300 K. Yeah. So if there is no heat loss at all, there's nothing about the heat loss or something like that. So what will be the value of this thermal time constant? How much the temperature of the sensor, like we can calculate with respect to, like, in terms of this time constant. You can say the like, uh, you can say anything. So like you can just use any kind of a convention as well. The sensor, when the sensor was like differently like placed in some place, the value was 300 K, but while we have attached it to and this object, let's say this is the object temperature, that is TO. So we need to know like what is the value of this sensor. Let's take about like maybe 2 3 minutes, 5 minutes. It's a very easy one from the like previous one itself. Just have some water and then we'll come back. How to connect these things, like let's say how to connect TS and TO. That's the main question here. How to connect these things? What is the connection among this? If we need to change the temperature of this sensor, which was previously obviously TS, that was 300, we need to get the, like, if we are attaching this with this temperature, like object temperature, so what will happen? There should be a shift of this, like from TS it should go to TO. So there should be a temperature addition or a temperature, like a change in temperature, let's say, nothing else. A change in temperature that we can maybe, um, let's say if like it's like needs temperature. So like let's say there's a change in temperature T, let's say TF. There should be a function of this TF. Mm, maybe I'll give the at least the equation because it'll be a bit easier. So we know the sorry, we know the basic equation of a sensor. The temperature was TS, and the change in this was Let's say it's del T, that the change in temperature, but there will be a temperature coefficient of this. This will be the equation. So now use it to the value of this. How to use this to calculate this? There are like several key points in the question as well. So it's already saying that heat loss in the environment is zero. What does that mean? Anyways, like del T is nothing but the change in like Ts minus T naught, or like it will be T naught minus Ts or something like that. So how to calculate this? Heat loss. What is the heat loss? Maybe do this. Ts is sensor temperature. T naught is jet temperature. Del T is change in sensor temperature. If there was a direct change, like if let's say that the object changed, sorry, the sensor changed the temperature of 5. So there won't be a case where the object is 100 and the sensor had 95. So sensor needs to increase the amount by plus 5. But there may be some kind of heat loss or something. So that this term effectively calculates that heat loss. So if there is no loss at all, so this term, what will happen to this term? If there is no loss at all, what will happen? Zero. Not exactly, just think about it. Because the T can't be zero, right? There should be a certain amount of temperature change in it. So like there is temperature. If there was no temperature change at all, and also the environment doesn't has a like heat loss or something like that, or some kind of a leakage, so it would have been zero. That's perfect. That would have been the perfect answer. But the temperature is anyways changing the temperature, because we already know the value of this was 300 K. So the temperature of the sensor is changing. So we can't say that e to the power 0 will be here. Hmm, Let me give you a hint. This will be minus 1, because the loss term, that is the that what do I say, tau, it will be equal to the value of the temperature change. So the temperature change and the loss term both will cancel each other out, and it will be e to the power of minus 1. So the formula will be nothing but Ts equals to T naught minus del T into e to the power of minus 1. Now you can calculate the answers. Give me the answer. And we already know that this value of, let's say, the maybe 300. Okay, so del t is t naught minus t naught minus of ts, let's say, with e to the power minus 1, then it would be t naught minus t naught plus ts e to the power of minus 1. So what will be the answer? Um, Sorry, it should be e to the minus 1. So if we move here, so the value of t naught would be 1 minus e to the power minus 1 plus ts into e to the power of minus 1 is the value of ts, the new value of ts rather, is the amount of, what is the value of e to the power minus 1? That's nothing but, this is nothing but 0.367. So this will be 0.632 into t naught plus 0.367 into uh, into nothing, just that's it, into the ts that would have been, yeah, into 300k. So that would be 367 into 300, that is 100, that will be 110.1 k plus 0.632 into t naught. This is the value of this. So this will be the value of this, but in the question we need to measure a different value, that is after one thermal time constant what will happen. So we have got this value minus 1, but what will happen with the value? Is it the correct answer or not? It is because we don't know the first value of the temperature of the object. So anyways, the temperature of the object will remain in the answer itself. So with the temperature of the object changing, the new temperature of the sensor will change accordingly. Okay, so we'll go to the next question. Which of the following statement is true? Let's go one by one. The first question is, the dynamic condition of thermal sensor follows an exponential relation. You can see it from the previous one itself. The dynamic condition is this. So it has an exponential term in it. So the first one is anyways true. The second one, higher time constant relates to a faster response. Is it true or not? If we have a higher time constant, so it should it give like a faster response of the sensor or not? Let me write it again. The del T is characterized as change in temperature with respect to T by tau. Ah, anyways, it's same T by tau. So with the higher time constant, should it give a higher response? Like this value should be a higher value, right? To increase this value, what should be the case? If we increase the time constant, that is the tau value, should it increase the del T? Any response? No, it shouldn't actually. Because if we increase the value of tau, what will happen? Let's say if like we have this value where like it is del T into e to the power of, let's say the time is constant, like let's say it's 1, just it's 1, and tau is 1, and in another case let's say tau is 5. What will happen? Which one is the higher one? This one or that one? But this has a higher time constant anyways, so it has a higher tau. This has a lower tau. Which one will have a like faster response? Then value of this is e to the power of minus 1. The value of this was 0.367 or maybe 8, and value of this is this. So what happens? This changes, that is the change in the temperature what we were measuring earlier, del T changes as it's a bit lower, so it will be lower change, but in this case it will be a bit higher change. What will happen to the response? Should it give a higher response because your temperature is changing anyways a bit faster? It shouldn't actually. So it doesn't always require that if you have a higher time constant the response will be faster. It is not like that. The next one is, to have a faster response, specific heat of the sensing material in the thermal sensor must be high. So the specific heat of the sensing material should be high because it is a correct one. Because what we need to know, if the thermal sensor, the thermal sensing material, it should be in the superior quality. What in the like what key parameters it has, that it depends on the like the sensing or the faster response time. If the like material changes the like with a very small amount of heat, that the specific heat of the sensing material changes, the response will be faster and faster. So it doesn't depend on the exactly the time it takes to like change the temperature, rather it needs the specific material properties, that is like the specific heat, to change faster to get a faster response. In a steady state, the final thermal resistance between the sensor and the object, okay, to for finite sensor can reach to the object temperature provided thermal conductance between sensor and environment is zero. We have already studied this question actually. So in the previous one itself, our main assumption was with the heat loss of zero in the environment, in this case as well, they have given that thermal conductance between the sensor and the environment is zero. Already they have given that it is a zero conductance state. So what happens that if can the sensor reach the object temperature? Yes, obviously it can reach, because from our previous answer we know that Ts new was nothing but 110.1 K with 0.632 into T naught. That is, it depends on the object temperature obviously, but it doesn't require that. Even if the object temperature can be like very high, it will still reach the temperature of the sensor will always reach the temperature of the object itself. It can take a very large amount of time. It can take it can just reach that within an instant as well, but it can reach. That's the answer of this question. The next question is this. So at steady state, we need a temperature sensor which is equal to the object temperature. So what will happen if we make the object temperature and the ambient temperature same? What will be the consequences? Let's say the environment temperature is T naught, whereas the object temperature is TB. The question is that, just, yes. So the question is that we need to make the temperature of the sensor equal to the object temperature, not the object and the ambient temperature. So how can we just take the temperature, temperature of the sensor equal to the temperature of the object actually? As we can see that to get this value, the temperature of the sensor to the temperature of the object, what we need, we can make the thermal resistance between the sensor and the object zero. That let's say there is no temperature drop in between this, like the TS, if it's let's say 100 degrees centigrade, whereas the object body is 105 degrees centigrade, the value can be directly transferred. So what will happen, the sensor will just come to the value of 105 degrees centigrade and there will be no loss. So that means there is no resistance. So the third one is a true one, where we can see that without any thermal resistance, the temperature of the sensor that was 100 degrees centigrade, after some time it will be 105 degrees centigrade. There won't be any issue. Other than that, what we can make the sensor to do that, the resistance of the environment and the sensor should be infinite. So if the temperature, as already we have, like, to make the sensor temperature equal to the object temperature, so what will happen if this and this was anyway same, exact same, what will happen, it won't be able to get the enough temperature from the environment to shift to that temperature of the object. So what we need to know that this resistance, the change in this temperature sensor and the the environmental temperature, it should be, the resistance should be infinite. So the sensor temperature can't never reach the value of the ambient temperature. So it has only the cases where it can reach the value of the object temperature. So both of these cases are true, and either one of these will work. So the final answer will be this, not this. Sorry, maybe I'll remove this. Yes, the final answer will be this. So there are two cases. In the first case, what we can do, we can just increase the thermal resistance of the sensor with the environment to infinite. So the temperature of the sensor can't even reach to the values of the environment. So it will anyways move towards the object temperature. Another case is that the temperature, sensor temperature, is like able to move to the object temperature directly without any resistance. So the third point is also true. So we can, what we can make is that if this is the sensor, this is your sensor, this is your object, and this is your environment. So if the distance between this is infinite, it can reach to this value, and if the distance between this is 0, it can reach the value of th to tb. This is the ultimate goal, that a sensor should be able to reach the value of the object directly, so that we need to, like, we can what do we say, like, precisely know the value of the object temperature. So in in case of thermal sensing, which one is true? First we need to know what is the equivalent circuit of thermal sensing, obviously. and I guess that was in the lectures itself. Fourth is not true. In which case, sorry, I just missed your answer. Actually, sorry. In which case you were saying the fourth is not true. Hello, yeah. Can I just explain in which case you were like saying that? I just missed that. Well, okay. Question six. Just wait a second. Question six. You were saying. Oops, sorry. You were saying that at steady state for final thermal resistance, sensor and object, sensor can reach to the object temperature provided thermal resistance between the sensor and the environment is zero. So you were saying that. Let's see. What was the question? At thermal at steady state for finite thermal resistance between sensor and the object. Okay. Sensor can reach to the object temperature. Yes, provided thermal conductance. No. Uh, just so here what we have already explained that in both of the cases this was talking about the resistance between these things. So the resistance between the object and the sensor should be infinite, or else the resistance between the sensor and the object should be zero or nearly zero or something like that. But in this question the main focus was on the conductance, just opposite of the resistance itself. So if the sensor and environment, that is the from TS to T of the environment, let's see TE here. So the resistance is nothing but infinite. There is an infinite yes, there is an infinite resistance between these things. So the conductance will anyway be zero. Yes, yes, directly from the equation itself. Let's say the second one. Let's talk about the second one maybe. So temperature difference is analogous to a potential difference in an electrical circuit. Is it or not? The first one is from the circuit itself, but it is a true one anyways. But the second one, temperature difference, wherever there is a temperature difference, it's analogous to a potential difference, that is the voltage divider or something. Sorry, voltage difference circuit equal to that. Actually, it is. It is exactly because we are going towards an equivalent circuit. We need to understand, like already understood phenomena, like the change in voltage or currents. We understand them very clearly. So to understand the phenomena using an thermal sensing setup, we need to get an analogy with another known parameter that can be voltage. Actually, voltage, the change in voltage is equal to the change in resistance in that equivalent circuit itself. A thermal capacitance is present between object and a sensor. Is it true? If there is a, let's say, a sensor and there is a capacitance between this, the question is what will happen? What will happen? There will be a capacitive effect induced within it. So in the equivalent circuit, we only have resistors. That's why there is no capacitance in between this. This is wrong. And in the dynamic response, that higher the thermal resistance between sensor and object, slower the response of the sensor. Is it true? We have already discussed this. So in the dynamic condition, the thermal sensor follows an exponential relation. Everybody knows that. But with higher time constant, there is faster response. Actually not. So this is also a true statement. We'll move towards the this the very basic statement. In a capacitive sensor, so if we introduce a dielectric material, effective electric field increases inside the dielectric as compared to the air. So it says that, like, if you have a parallel plate capacitor, first it was here only the air, and in the next case there is a dielectric material in between it. Is it true? Actually not. It's not. So the minimum value of relative permittivity is 1. Yes, like it's a direct relation. The minimum can be 1 because the minimum is the air permittivity. The minimum value of relative permittivity is 0. It can never be 0. After the introduction of a dielectric material, effective electric field decreases. Oh, ah, it's the same. Yes, it's a yes. So it's a bit harder one. So we have a coaxial capacitive sensor here. We know that height is 100 centimeter. It's already given here. The ratio of the outer and the inner radius, that is RB by RA, equals to 2, where RB is the outer one and RA is the inner one. So we just applied a DC source voltage of 10 volts is the voltage, and a constant current of 6.5 nanoampere flows through it. Here you can see this is the water level, right? So we need to know what is the speed of the water level rising, and there is no like losses with the interfacing circuit with the sensor itself. So there are no losses. It's already given here. External circuit has zero resistance, so there are no external losses. There are no direct losses actually. I'll give maybe 2-3 minutes because we don't have that much time left. So I'll give maybe 3 minutes maybe. Just have some water. Anybody trying? Or should I give you some hint? Maybe I'll give you some hint. I am removing this. First of all, what we need to know to solve this equation is the value of this uh, capacitor, right? So C is nothing but 2 pi epsilon naught into epsilon r, that is the value of epsilon, and ln of the ratio of the radius of both of the coils, right? And we know epsilon naught is nothing but 8 point why 854 into 10 to the minus 12 with the units or something like that. And epsilon r is given in the equation. That was 80. I missed it, but let's say this is epsilon naught. This is the value. So like, just give me the idea to how to move towards solving this question. First, we need to know what is the charge generated, right? That is nothing but C into V. That is now how to solve this. We also know. Let me give you another hint. Maybe I is nothing but dq dt, change in the charge with respect to time. Let me maybe solve this. Yeah. So dq dt is what? Dq dt is ddt of the value c into v. So we'll get the value of c dv dt plus v into c dc dt, right? Is the values. So here we know there is no change in voltage because this is a DC voltage already applied there. So there is no change in voltage. So dv dt will be 0. So the value will be V into DC into dt. We know the value of V here. So we'll get to know now. So the capacitance of the sensor will be, that is C 2 pi into, we already know the value of epsilon naught and epsilon r, divided by, sorry, divided by ln of Rb by Ra. We already know that value as well, that is nothing but 2, right? So here we need to know that capacitance of the sensor itself. So what will happen, that in this case there will be up to, just wait a second, up to here, if this is in 2D. So here for this part itself there will be a different epsilon, right? And for this part it will, there will be a different epsilon. So we'll remove the epsilon r here. So if this is let's say the epsilon of w and that is epsilon naught, so what will happen, sorry, what happened, still recording, right? Yeah. So what will happen for the first case, that the case with here itself, there will be just a single value of air, that is nothing but 1 into, this will be 1 because we anyways we have the epsilon naught outside. So it will be nothing but 1 minus the length, that is L, okay? And um 1 minus the, let's say no, let's say this as this as the L1 and this as the L2, the length of these things, okay? So L1 plus L2 we already know, that is the value of this. So let's say this is L1, 1 minus L1 itself, and the other part will have the water. So the value of epsilon r will be here into the value of this L1. So let me take my calculator. Yes. So it will be sorry, it will be 80.22 into 80 into L1 plus 1 minus L1, and everything will be into 10 to the minus 12. Okay, so this is the value. Maybe I'll go towards the next slide itself. I should have taken piece remaining, let's say. Okay, now we need to know the value of Q, right? So we know the value of uh, let's say first we need to get the values. So what was the value again? It was this. uh, we can adjust another line here. So what will we do, that will get to know the value of dc by dt. We need the change in that, so we'll just divide it. So it will be 0.22 to 10 to the power minus 12. Let's just remove these things. 80 into dl1, change in l1 with respect to time, and there should be dl1 with dt, right? Because anyways one is getting eliminated. So we'll move towards the next page. So here what we can write, that dc dt we have found out that is 80.22 into 10 to the power minus 12 into 79 into dl1 by dt, right? Now, so we need to know the change in water level, right? So how to measure the change in water level? So the change in water level is dl1 by dt. The change in water level, the water level, let's just go towards that previous page. So as we have measured this, the L1 as the change in the water level. So we need to know the change in uh, L1, that is that dl1 with respect to time, that is the dl1 by dt. So we need to know this. So it is nothing but so how much is it? It is 0.65 into 10 to the power minus 9. That is the value of dc by dt, as we already know from the question itself. And this will be 80.22 into 10 to the minus 12 into 79. So let me calculate this. 80.22 divided by 10 to the minus 12 divided by 79. So the value will be nothing but 0.10256 meter per second. And so like if we just convert it, that will be 25 centimeter per second. So this is the change in water level, that is L1 with respect to time. Just wait a second. So here we knew the value of this, right? So that is the change in what do I say, like from here we already know that, right? So Q is V into dc by dt, right? So here if we go here, dl by dt, we can say that by measuring the value of dl by dt, it is by dc by dt. So like 80 point something these things, dc by dt we know the value already, that is the 0.65 nano ampere. So this is the value. So this is the change in water with respect to time. This is the change in water level. So what we get to know from this question was that using a capacitive sensor, we can measure the value of water level change in a tank, or in like maybe you can say a container. Obviously, like everybody knows, like this kind of a container we use, right? Because the plastic has its own thickness. So because of that, we have to compensate that value. It is not in just a thin level of plastic. We have like this double layered plastics, right? So to like compensate the values, we need to get the exact accurate value of water level change, and by this method we can do this. So this was a hard one actually. So maybe in the next class itself, like we can discuss about this. So anybody has any questions regarding this? Any problem to understand this thing? Nothing. Yeah, so actually my last question was this one, but I forgot to set that. So my last question was, what is the sensitivity of this like sensor? So like the last sensor, I have to calculate the sensitivity of this sensor. So what is it? So maybe we'll do it in the next class. We'll just continue the previous thing and then we'll talk about this in the next class. So thank you everyone for attending this session. And if you have any queries regarding this thermal sensors and capacitive sensors, we'll also maybe will have at least 10 minutes to discuss about the problem, like if anybody has any questions or something like that. Yeah. Thank you.